Here we are looking at optics, the dynamics, preamble. Let's set the problem up. Here's the medium 1. Here's medium 2. The boundary is at x is equal to 0. We have an incoming wavefront of electric and magnetic fields. It's reflected. There it is. And we know from the previous kinematic studies that theta I equals theta R, billiard ball reflection. And we know what theta T is from Snell's law. So we know that N1, if N1 is the index of refraction of material 1, N2 for material 2, N1 sine theta I is equal to N2 sine theta T for transmit. And the point is that we already have this kinematic information. We don't have to redo it. We will find that this comes up in the dynamics. So what do we mean about dynamics? Well, we want to now actually calculate the amplitudes of the reflected and transmitted fields. And in order to do that, there are two things we need. One is we have to be able to represent the plane wave for the electric and magnetic fields. And we're going to do that starting with the incident plane wave. And then we have to figure out how much of that amplitude is associated with reflection and how much of it is associated with transmission. To do that, we have to do something called boundary condition matching. And we'll look at that in more detail. But before we get into the details of the boundary conditions, I want to represent each of the waves in terms of what we know as exponentials and give us a bulletproof way of doing this. So we'll never get confused about plus signs and minus signs. And that relates to previous work we've done in class. Continuing on with optics, the dynamics phase. What we're going to do is look at a plane wave that's coming in from here, going down to hit the boundary. And this is material 1, and that's material 2. What we want to do is set this up. And in particular, we want to write the form of the electric field. We're always going to remove the time dependence. So we're just going to look at the spatial part of this relationship. There's the vector amplitude. We've done this before. And the spatial part is e to the minus jk dot r. There's our plane. Now, why are we doing it like this? Why not a plus sign? Well, if we put in the time dependence, e to the j omega t minus k dot r. As r increases or decreases, time evolves. Now in this case, the plane is moving in this direction. It's in the direction of increasing x and increasing z. K is the normal, so as long as we fix k, the problem is solved. The only thing that's left to discuss is why it's a minus sign, and to do that, we go back to our one-dimensional idea that we did right at the beginning of the course, f of z minus vt, or if you want, factor out the minus v, and you can write it like this. So as time increases, z increases, divided by v, so this argument of the function stays the same, or equivalently, the phase is the same. So we're just looking at the phasor part always. When you see something like this, it's phasor. Now, let's look at the picture. Now that we got the math out of the way, this is the form for E, and here's our wave. So there's the front of the wave. It's a peak. And it's moving in this direction. So it's moving in this n hat direction. There's our k vector. As we saw in kinematics, can be resolved into a lateral horizontal component along the z direction and a normal component along the x direction. And we, just as a reminder, we saw that we could get Snell's law by matching the horizontal component of the wave vector k for the incident, transmitted, and reflected waves. Now what we have to do is write the same relationships for the other waves, but there's one final thing to talk about, is this vector amplitude E. So basically, as time evolves at a fixed location, we have an oscillation in time in this direction. If we fix the position, the E vector is going to eventually go to 0 and go in the other direction. So it's vibrating perpendicular to K. Conversely, H would be sticking out of the board, so coming at my forehead. And then, of course, as we take the cross product, as we saw, we go in the K direction, and that's where the energy goes. E cross H gives us the direction of K. So now we have to repeat this for the other waves. So we'll do exactly the same. It'll be this form. There'll be a different amplitude here. This will be the same. The only thing is the components of K will change, as we'll see. Here, the components of K in the Z and the X direction are both positive. When we go in the transmitted domain, they will be positive, and something else in the reflection domain.